Welcome to my channel. This is scikit-learn. In this tutorial, we will discuss about principal component analysis. Principal component analysis is a method for reducing dimensionality of a dataset that improves visualization, and we can short the number of variables to a few number of principal components. So it is basically a non-dependent procedure where we have no dependent variable. We just construct different principal components based on a large number of variables. So the main task in principal component is to select a subset of variables from a large data set based on which original variables have the highest correlation with the principal components. You can check that as well. And we also see the pattern in a data set, and we can in exploratory analysis, we can extract features based on principal components. When we have a large number of variables, we can just short them to a few number of principal components that captures almost a large proportion of variability in their data set. So it reduce noise and make a better visualization. And you can also read about principal component analysis in different books. This tutorial consists of implementation of principal component to a data set. That is a heart disease data set I have taken from Kaggle. We just need to import the data using pandas library, and I have already uploaded heart.csv data here, and then we can just use the command pd.read underscore csv and then content. You don't need to write the content. You can just import using the dataset name. So now we get the first few observation of the data set, and then we also see the information, the type of all data sets that are few are integer, 64 data integers, and some are floats that can be any number, and some I think we have some characters as well. If not, then okay. Now we will handle the missing values. For that, we need to do some data pre-processing. For data pre-processing, we need standard scaler that is used to standardize the data, and one hard encoder that is used to convert the categorical variables into dummies, as we already discussed. And then column transformer, that is basically just a pipeline function that the function will be applied to every column in our dataset. And the pipeline is basically uh, we are basically passing through all dataset from that pipeline. And if you are R user, you must know about this function. And this is just same as the pipeline in Python. So we now identify categorical and numerical columns. So we created data sets, one with objects when the data type is object, and the other is when data type is integer 64 and float 64. So we are excluding the target variable that is basically the heart disease status. So we just exclude that to make analysis simple. Basically, we are not interested in the status. We are basically stratifying or making extracting the features from the set of risk factors that are related to heart disease status. So we can run this command and this command. Now the numerical transformer, that is for numerical values, we just standardize them using standard scale function. And categorical transformer, that is that will basically make the categorical variables as dummy, and when and the category is unknown, basically there are missing categories, then those categories will be ignored. So you can write handle unknown is equal to ignore. Then and now you can create a column transformer to apply different transformer to different columns. So pre-process column transformer, then we are using two transformers number for numerical transformer, that is this function, and the columns are numerical features, this one. And categorize, that is categorical transformer and categorical features. So we are just applying the transformer, this transformer to numerical features, numerical columns, and these features to this transformer to categorical features, and that are converting to different dummy variables. Now we just applied preprocessor, and then we apply pipeline steps, preprocessor and preprocessor. Basically, this is just name preprocessor, and this is the function basically we are applying. So and then df preprocess final pipeline dot fit transform means we are basically applying this function, and we get fitted values using this pipeline function, and we are applying this pipeline to our data set, that is we named as df, I think we already named it as df. So this is our df process, means it is processed data set. You can just run it, and if you want to display it, you can display as well, right? Just display and then uh, df processed. It's giving some error. We can import and try this one. Still the head function is not working for this data set. I don't know, this is it for, I think, a different data type, that's why the head command is not working here. So you can check with this. So this is basically an array, not a data frame, that's why the head command is not working here. So this is our pre-processed data set. Now from scikit-learn decomposition, this is basically within scikit-learn a library, we import principal component analysis. So there are a lot of functions within this library. So we are importing principal component analysis, and then we are applying PCA, and we need to set number of components. So in start, we just keep number of components to number of variables in our data set. So as many as we have, number of observations, we will get number of components, and PCA fit, and then we just put the processed data set. So it's giving 13 components, and then analyze and visualize the PCA results. So what we need to visualize, we need to compute the explained variance ratio. Basically, when we talk about principal components, we need to capture all the variation in data into when we are just transforming data to another dimension. For example, we have XY plane, we are converting it into uh, uh, WZ plane, for example. So for transform data, we need to check how many proportion of data has captured in the principal component. So we need to check for different number of principal components. The extreme case is the case we have, for example, we have 14 number of variables, 13 number of variables, and we will get 13 number of principal components. So we need to decide how many principal components are important. That is based on the proportion of a ratio of variation explained by that component. So we need to just make a this plot is known as scikit plot. We need to make a scikit plot to see the proportion of variation when we keep different number of explained different number of principal components and see how explained variation is changed. So we will do that. First, we need to find the explained variance ratio. That is, within PCA, we have explained variance ratio. This function, you will get the explained variance ratio. And then calculate cumulative explained variance ratio. We need to just sum up the explained variance ratio for all principal components. And within NP library, we have this. Now we will need to plot these two, the number of components versus explained variation ratio. So we will set a plot with size this, and then PLT plot range is from 1 to number of explained variation ratio plus 1. For example, explained variation ratio is 0.9, so we will get 1.9. The value will be 1.9 and so on. And then explained variation ratio, this is just the range of the x-axis. And on x-axis, we have explained variation ratio and mark 0 line style and explained variation ratio we will label it. And then range onto this cumulative explained variation ratio. We will plot these two for the x-axis with this range. This is just number of explained ratio plus 1. For example, if we have 10 principal components, we will have 11, 1 to, we will just draw 1 to 11, and same as with this. And we are plotting these two, one explained variance ratio and one cumulative explained variation ratio. And then we will just give a title, we will just give the X label, data, number of principal components, and then PLT Y label explained variation ratio. Now we will give X ticks to the range 1 to number of explained variation ratio plus 1, and then we are giving no legend, and then PLT grid is equal to true. We want to display the grid as well, and then PLT show. So you can see this plot. This is the plot. Principal component and explained variation ratio. This is explained variation. This is cumulative explained variation. This is basically adding the explained variations. For example, if we add this plus this, 0.2 plus for example, 0.18, then it will give 0.38, for example. So this is adding this, and then again we add this, it will go up. So this is cumulative explained variance, and this is original explained variation ratio for each component. So we will see when we keep only one component, it will explain the 20% variation in data. When we keep two components, it will the explained with ratio is uh, basically for component one, the explained ratio is this, and but when we add components, it will goes increasing, and this is the increase. And when it goes up to just this straight line, then we will say that adding further component is will not make sense, so we will just cut the number of components to that. And in some books, we will just see the number of the explained variation ratio just here. When it touches, for example, below 0.1, we will stop. And in some books, we see the number of we see the lambda, that is 1 over explained variation ratio, or then the value of lambda less than 1. For example, we will just exclude those principal components from the analysis. So TFPCA, PCA transformed, and we just we create a data set for PCA, and that is PCA transform, and then DF process. So we just obtain the transform data with principal components, and then we can show the dimension of the transform data as well. The transform data has again the 13 variables, all the 13 variables we included, and 303 observations. So can just run this. Now, if we want to decrease number of components, for example, we want to transform data with here there is an optional plot, that is a scatter plot between two components, principal component 1 and principal component 2, and we just try to see how there is how the two sets, one with basically we are using the target variable, so one with no heart disease and one with heart disease. We just can see the relationship between two principal components, and we can see this relationship by heart disease status. So we can do this again. If PCA shape is greater than equal to 2, means number of components is greater than equal to 2, we will just get we are just taking basically a number of PCAs only 2. And then if we have only one PC, then we will not get this plot. And then we are using DFPCA, the first principal component, and then second principal component, and then the color variable is the target, that is heart disease status, and then the map color, and this is alpha. And this is just a map characteristic. We can just skip it as well. And PCA of heart disease data, this is title, and this is X label, and this is Y label, and we can just label this heart disease. So just this is heart disease status, and this is first component, and this is value of the second component. And we can extract the number of features, for example, important features. So based on this plot, this is based on the explained variation, we are keeping 12 number of we want to extract only 12 components from this data set, so we keep number of components is equal to chosen is equal to 12. We can convert it into 10 as well. And then this is final PCA data. PCA number of components is equal to this. We run again PCA with 10 number of components, and then we get the final number of features from the transform data, and then we will just see the number of dimension of this dataset. So this is a dataset. It can display here final features. So this is your final dataset with the extracted number of extracted features. So this is all about principal components. The dataset contains 918 observation with 10 columns, and the principal component was applied to pre-processed data and based on the cumulative explained variance plot. This is also called cumulative explained variance plot, and this curve is called Sikri plot. Basically, when we construct this based on uh, eigenvector eigenvalues in the principal component analysis. So thank you so much.